Welcome to today's session. In this problem, we'll tackle problem number 1968, array with elements not equal to average of neighbors. This is a fascinating challenge that tests our grasp of array manipulation and problem-solving strategies. Let's dive in and explore the steps to approach and solve this problem effectively. In this problem, we are given a zero-indexed array of integers called nums. The goal is to rearrange the elements of nums in such a way that, for every index I between 1 and nums.length 2, the value at nums, I, is not equal to the average of its two neighbors. In other words, the value at position I cannot be the result of averaging the values at I1 and I plus 1. The problem guarantees that at least one valid rearrangement of the array exists. You need to return any rearrangement of nums that satisfies this condition. The input is given as a list of integers, and the output should also be a list of integers representing a rearranged version of nums that meets the required condition. Let's go through an example to understand how the condition is applied. Suppose the input array is 1, 2, 3, 4, 5. A valid output is 1, 2, 4, 5, 3. Here's why: for index I equals 1, the value at nums, 1, is 2. The average of its neighbors, nums, 0, plus nums, 2/2, is 1 plus 4/2 equals 2.5, which is not equal to 2. For index I equals 2, the value at nums, 2, is 4. The average of its neighbors, nums, 1, plus nums, 3/2, is 2 plus 5/2 equals 3.5, which is not equal to 4. Similarly, for index I equals 3, the value at nums, 3, is 5, and the average of its neighbors is 4 plus 3/2 equals 3.5, which is not equal to 5. Since this arrangement satisfies the condition for all valid indices, it is a valid output. Here's another example. If the input array is 6, 2, 0, 9, 7, a valid output could be 9, 7, 6, 2, 0. Let's verify this arrangement. For index I equals 1, the value at nums, 1, is 7, and the average of its neighbors is 9 plus 6/2 equals 7.5, which is not equal to 7. For index I equals 2, the value at nums, 2, is 6, and the average of its neighbors is 7 plus 2/2 equals 4.5, which is not equal to 6. For index I equals 3, the value at nums, 3, is 2, and the average of its neighbors is 6 plus 0/2 equals 3, which is not equal to 2. Since this arrangement meets the condition for all valid indices, it is also a valid solution. Now let's look at the constraints and edge cases. The array must have at least 3 elements, and it can be as large as 100,000 elements. Each element in the array is between 0 and 100,000. The problem guarantees that a solution always exists, so we don't need to handle cases where no valid rearrangement is possible. For edge cases, consider an array of the smallest size, such as 1, 2, 3. A valid output could be 1, 3, 2. If all elements in the array are the same, such as 5, 5, 5, 5, any rearrangement satisfies the condition because the average of the neighbors will always equal the middle value. For very large arrays, the algorithm must be efficient enough to handle up to 100,000 elements. Finally, if the input array already satisfies the condition, no rearrangement is needed. To solve this problem, let's first consider the brute force approach. The idea here is to check all possible permutations of the input array and verify if each permutation satisfies the condition that for every index, the element at that index is not equal to the average of its neighbors. This can be achieved using a library function like itertools.permutations in Python to generate all permutations of the array, and then checking the condition for each one. However, this approach is computationally expensive. Generating all permutations of an array with n elements involves n operations, and for each permutation, we need n checks to verify the condition. This results in an overall time complexity of n*, which becomes infeasible for larger arrays. Clearly, a more efficient approach is needed to handle this problem effectively. To optimize the solution, we can use a strategy that involves sorting and rearranging the array. The key observation here is that in a sorted array, adjacent elements are more likely to produce averages that match other values in the array, which violates the condition we need. To break this relationship, we can rearrange the array in a specific way. First, we sort the array. Then, we split it into two halves, the smaller half and the larger half. Finally, we interleave the two halves in an alternating pattern, where elements from the smaller half occupy even indices, and elements from the larger half occupy odd indices. By alternating smaller and larger values, we disrupt the alignment that could lead to an element equaling the average of its neighbors. This ensures that the condition is satisfied. Now let's analyze the complexity of this optimized approach. Sorting the array takes n log n, which is the most computationally expensive part of the process. Splitting the array into two halves and interleaving them can be done in n time. Therefore, the overall time complexity of this approach is n log n, which is significantly better than the factorial complexity of the brute force approach. This makes it scalable for larger inputs. We selected this strategy because it avoids the inefficiency of generating permutations and leverages the properties of sorted arrays to achieve the desired result in an elegant and computationally efficient way. When comparing the brute force and optimized approaches, the brute force method is straightforward but impractical due to its factorial time complexity. In contrast, the sorting and rearranging strategy is efficient, reducing the complexity to n log n. This approach hinges on the idea that interleaving smaller and larger halves disrupts the alignment of averages, which is generally true, though testing edge cases, such as arrays with duplicate values, is important to confirm its reliability. One key insight that simplifies the problem is recognizing that the task boils down to breaking the alignment of values in a sorted array. By alternating smaller and larger elements, we effectively ensure the condition is met without resorting to trial and error. This realization allows us to move from a brute force solution to a deterministic, scalable approach. The goal of this problem is to rearrange the array such that no element is equal to the average of its two neighbors. More formally, for each index I where 1 equals I equals nums.length 2, the condition nums I equals nums I1 plus nums I plus 1 / 2 must hold true. One basic way to approach this problem is through brute force. In this approach, we generate all possible permutations of the array and check each one to see if it satisfies the condition. To do this, we first use a backtracking algorithm to create all permutations of the input array, storing them in a list. Then, for each permutation, we validate whether it meets the condition by iterating through the array and checking if the value at index I is not equal to the average of its neighbors. If any index fails this condition, the permutation is discarded, and we move on to the next one. This method ensures correctness but is computationally expensive due to the sheer number of permutations that must be evaluated. Once we generate all permutations, the next step is to identify the first valid permutation that satisfies the condition for all indices. If such a permutation is found, it is returned as the result. However, if no permutation meets the criteria, we return an empty list or indicate failure. There are some key insights to consider here. First, generating permutations is an expensive operation with a time complexity of n, as the number of permutations grows factorially with the size of the array. Second, checking each permutation for validity involves iterating through the array, which adds an n cost per permutation. This makes the brute force approach impractical for larger arrays. Additionally, there are edge cases to consider. For example, if the array has fewer than 3 elements, the condition is trivially true, as there are no indices that fall within the range 1 to nums.length 2. On the other hand, if all elements in the array are identical, no valid permutation can exist. These challenges highlight the need for optimization to make the algorithm more efficient. To implement the brute force approach, we rely on several key data structures. The input array serves as the base for generating permutations, while a list is used to store all possible permutations for evaluation. During the validation process, we use intermediate variables to calculate the average of neighbors and track the current index. However, given the factorial time complexity of generating permutations, optimizations are necessary to handle larger arrays. One potential optimization involves sorting the input array to reduce duplicate permutations and applying a two-pointer technique to generate combinations more systematically. Another approach is to use a greedy algorithm to construct a valid arrangement directly, without generating all permutations. For instance, we can split the array into two halves, one with smaller elements and the other with larger elements, and interleave them to minimize the likelihood of any element being the average of its neighbors. These strategies aim to reduce the computational overhead while still ensuring correctness. In addition to sorting and greedy methods, we can leverage mathematical properties to further optimize the solution. By analyzing the condition nums I equals nums I1 plus nums I plus 1/2, we can deduce patterns that help avoid violations, such as arranging the array in an alternating or zigzag pattern. This ensures that the difference between consecutive elements is sufficient to prevent any element from being the average of its neighbors. Now, let's analyze the complexity of the brute force approach. The time complexity is dominated by the generation of permutations, which is O(n), and the validation step, which is O(n), for each permutation. This results in an overall time complexity of O(n). *n. The space complexity is O(n) as well, due to the storage of all permutations. To better understand this process, let's walk through an example. Suppose the input array is nums equals 1, 2, 3. First, we generate all permutations of the array, which are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Next, we validate each permutation to find the first one that satisfies the condition. Starting with 1, 2, 3, we calculate the average of neighbors for I equals 1, which is open parenthesis 1 plus 3 close parenthesis divided by 2 is equal to 2. Since this equals nums 1, the permutation is invalid. For 1, 3, 2, we check the average for I equals 1, which is open parenthesis 1 plus 2 close parenthesis divided by 2 is equal to 1.5. This does not equal nums 1, so the condition is satisfied. Since this permutation meets the criteria for all indices, we return it as the result. The final output is 1, 3, 2. By following this step-by-step process, we ensure that the solution is correct, though the inefficiencies of the brute force approach make it unsuitable for larger input sizes. This underscores the importance of exploring optimized strategies for real-world applications. This solution rearranges the input array such that no element is equal to the average of its neighbors. The key idea is to sort the array first, which ensures that smaller elements are grouped together and larger elements are grouped together. By interleaving these groups, placing smaller elements at even indices and larger elements at odd indices, we can guarantee that the condition is satisfied. Explanation of the code. 1. Sorting the array *. The input array is sorted in ascending order. This ensures that elements are arranged from smallest to largest, simplifying the process of interleaving smaller and larger elements. 2. Creating the result array *. An empty array of the same length as the input is initialized to store the rearranged elements. 3. Placing smaller elements *. The smaller half of the sorted array, from the start to the middle, is placed at even indices 0, 2, 4. This step ensures that smaller elements are distributed throughout the array. 4. Placing larger elements *. The larger half of the sorted array, from the middle to the end, is placed at odd indices 1, 3, 5. Placing these elements at odd indices ensures that the larger values are interleaved correctly with the smaller values. 5. Returning the result *. Finally, the rearranged array is returned, satisfying the condition that no element is equal to the average of its neighbors. Complexity analysis. Sorting *. Sorting the input array takes O(n) log n time. Rearranging *. Filling the result array takes O(n) time. Overall, the time complexity is dominated by the sorting step, making it O(n) log n. This approach is efficient and works for all valid inputs, as it systematically avoids placing elements such that the condition is violated. Here, we begin by importing the necessary Java utilities, then define our solution class and the rearrange array method. The first step inside the method is to sort the input array, nums, in ascending order using arrays.sort. This ensures that the smaller elements are grouped at the beginning of the array while the larger elements are at the end. Next, we create a result array of the same length as nums. This will hold the rearranged elements. To facilitate the rearrangement, we calculate the midpoint of the sorted array. This midpoint helps us divide the array into two halves, the smaller half, which will be placed at even indices, and the larger half, which will be placed at odd indices. We then use a loop to iterate through the smaller half of the array and place its elements at even indices in the result array. The index variable, starting at 0, is incremented by 2 after each insertion to ensure proper placement. After completing the placement of the smaller half, we reset the index to 1 and begin inserting the larger half of the sorted array into the odd indices of the result array. Similar to the previous loop, we increment the index by 2 after each placement to maintain the correct spacing. Once all elements have been placed into their respective positions, we return the result array. This ensures that no element in the final arrangement is equal to the average of its neighbors, satisfying the problem's requirements. With this implementation, we achieve the desired output efficiently and in a structured manner. To solve this problem, we first sort the input array. For the example where nums equals 1, 2, 3, 4, 5, the array is already sorted, so it remains as is. Next, we create an empty result array of the same length as nums, initialized with zeros. This ensures we have a placeholder for each position in the final output. The key idea of the solution is to rearrange the elements such that no element is equal to the average of its neighbors. To begin, we place the smaller half of the sorted nums array into even indices of the result array. The midpoint of the array is calculated as the integer division of the length by 2, which gives us 2. The smaller half of nums, which is 1, 2, is then placed at indices 0, 2, and so on. At this point, the result array looks like 1, 0, 2, 0, 0. Now we focus on placing the larger half of the sorted nums array into the odd indices of the result array. The larger half, which is 3, 4, 5, is assigned to indices 1, 3, and so on. This ensures that all elements are positioned in a way that meets the problem's requirements. After placing these elements, the result array becomes 1, 3, 2, 4, 5. This arrangement guarantees that no element equals the average of its neighbors. For instance, the neighbors of 3 are 1 and 2, and their average is not 3. Similarly, for all other elements, the condition is satisfied. This is the final output for this example. Moving on to the next example, we are given nums as 6, 2, 0, 9, 7. Starting with this new array, the first step is to sort it. After sorting, nums becomes 0, 2, 6, 7, 9. We then create an empty result array, initialized with zeros, just like before. The result array at this point is 0, 0, 0, 0, 0. Next, we identify the smaller half of the sorted nums array. The midpoint is calculated as 5 divided by 2, which equals 2. The smaller half, which is 0, 2, is placed in the even indices of the result array. This means positions 0, 2, and so on. After this step, the result array updates to 0, 0, 2, 0, 0. Then, we handle the larger half of the array, which contains the elements 6, 7, 9. We place the larger half of nums into the odd indices of the result array. This involves assigning the values 6, 7, 9 to positions 1, 3, and so on. Once this step is complete, the result array becomes 0, 6, 2, 7, 9. This arrangement ensures that no element is equal to the average of its neighbors. For example, the neighbors of 6 are 0 and 2, and their average is not 6. Similarly, for all other elements, the condition holds true. This gives us the final output for this example. Now, let's look at another example where nums equals 10, 1, 2, 9, 5, 6. For this array, the first step is to sort it. After sorting, nums becomes 1, 2, 5, 6, 9, 10. We then create an empty result array of the same length, initialized with zeros. At this point, the result array is 0, 0, 0, 0, 0, 0. Next, we calculate the midpoint of the sorted array, which is 6 divided by 2, giving us 3. The smaller half of nums, which is 1, 2, 5, is placed into the even indices of the result array. This means positions 0, 2, 4, and so on. After placing these elements, the result array updates to 1, 0, 2, 0, 5, 0. Then, we move to the larger half of nums, which consists of the elements 6, 9, 10. The larger half of nums is placed into the odd indices of the result array. This involves assigning the values 6, 9, 10 to positions 1, 3, 5, and so on. Once this step is complete, the result array becomes 1, 6, 2, 9, 5, 10. This final arrangement ensures that no element is equal to the average of its neighbors. For instance, the neighbors of 6 are 1 and 2, and their average is not 6. Similarly, for all other elements, the condition is satisfied. This demonstrates how the approach works for different input arrays, consistently achieving the desired result. To analyze the time complexity of the rearrange array function, we can break it down into its individual steps. The first step involves sorting the input array using the nums.sort operation. Sorting is performed using algorithms like timsort, which have a time complexity of O, n log n, where n is the length of the array. Next, we allocate memory for the result array with the statement result equals 0 *len nums. This involves creating an array of size n, which is a linear operation with a time complexity of O, n. Finally, we place the smaller half of the elements into the even indices of the result array using result, (2 equals nums, mid). Here, slicing nums, mid, and assigning to result, (2) requires copying approximately half the elements of the array, which also takes O, n, time. Next, we place the larger half of the elements into the odd indices of the result array using the operation result, 1, 2 equals nums, mid. This involves slicing nums, mid, and copying the other half of the elements into the array, which is another O, n, operation. When we combine all these steps, the dominant term in the time complexity comes from the sorting operation, which is O, n log n. The subsequent steps, such as array creation and element placement, are linear operations and do not affect the overall complexity significantly. Therefore, the total time complexity of the function is O, n log n. Moving on to space complexity, the memory usage is determined by the operations performed during the function. First, the input array nums is sorted in place, which means no additional memory is allocated for sorting. This results in a space complexity of O1 for the sorting step. Now, let's consider the space used for the result array. A new array of size n is created to store the rearranged elements, contributing O, n, to the space complexity. Additionally, temporary slices are created when we perform operations like nums, mid, and nums, mid. These slices each contain approximately n/2 elements, and they are temporarily stored in memory. Together, these slices add up to O, n, space usage. When we combine all these factors, the dominant contributor to space complexity is the result array and the temporary slices, both of which are proportional to the input size n. As a result, the overall space complexity of the function is O, n. To better understand the efficiency of the algorithm, we can analyze the best, average, and worst case scenarios. In the best case, the input array might already be sorted, but since the sorting step is always performed, the time complexity remains O, n log n. For the average case, the sorting step still dominates the complexity, making it O, n log n. Similarly, in the worst case, such as when the array is sorted in reverse order, the sorting step still determines the overall complexity, which is O, n log n. This consistency in time complexity across all cases highlights the efficiency of this approach. Comparing this to a naive solution, where we attempt all permutations of the input array and check if the condition is satisfied, the time complexity would be O, n * n. This is infeasible for even moderately sized arrays. In contrast, the optimized solution achieves O, n log n, time, which is both efficient and scalable. Finally, let's summarize the mathematical reasoning behind the big O complexity. The sorting step is the most computationally expensive operation, with a time complexity of O, n log n. Other operations, such as creating the result array and performing slicing, are linear in nature, with a time complexity of O, n each. However, these linear terms are insignificant when compared to the sorting step. When combined, the overall time complexity is determined to be O, n log n. Similarly, for space complexity, the result array and temporary slices each contribute O, n, to memory usage, making the total space complexity O, n. This solution is both optimal and scalable, making it far superior to any brute force alternatives for solving this problem. When solving this problem, there are a few common mistakes to be aware of that can lead to issues in your solution. First, overlooking edge cases is a frequent error. This might include failing to handle scenarios like an empty array, a single element array, or inputs with duplicate values. These edge cases test the boundaries of your solution, and skipping them can result in runtime errors or incorrect outputs during testing. Next, using inefficient algorithms for large inputs is another pitfall. For example, a brute force solution might work for small arrays but would fail for input sizes greater than 10,000 due to time limits or memory overflows. Finally, misunderstanding problem constraints can also lead to inefficiencies. For instance, not recognizing that the input might already be sorted or contain unique elements might cause you to overcomplicate your solution or miss opportunities for optimization. Paying close attention to these details is key to crafting a reliable and efficient solution. Another area where mistakes are frequently made is in recursion. Forgetting to define proper base cases or writing them incorrectly can lead to infinite recursion or outputs that are just plain wrong. This is why it's so important to carefully verify your base cases before diving into the recursive logic. Off-by-one errors are another common stumbling block. These occur when your loop bounds are slightly off, for example, iterating from 0 to n instead of stopping at n1, or when accessing indices that are out of bounds. Such errors can cause runtime exceptions that derail your solution entirely. On the interview front, there are some strategies that can help you stand out. Start by discussing the brute force approach, then move on to optimizations. Interviewers highly value a clear thought process. Recognizing common problem patterns, like sliding windows or binary search, can also help you quickly zero in on efficient strategies. As you code, explain your thought process step by step, especially when transitioning between approaches. Finally, always test your solution with edge cases during the interview to show that it's robust and complete. When it comes to related problems, there are a few worth noting that can help you build the skills needed for this challenge. For example, LeetCode 46, which involves generating permutations, is a great way to practice brute force approaches. LeetCode 47 adds the twist of handling duplicates, which introduces optimization challenges that are directly applicable here. LeetCode 39 focuses on generating combinations with constraints, and LeetCode 90 emphasizes subset generation where duplicates must be carefully managed. As for alternative approaches, backtracking is often a useful method for systematically exploring all possibilities while pruning invalid states. Though more efficient than brute force, it still has exponential time complexity in the worst case. Dynamic programming, when applicable, can help avoid redundant computations by caching results, though it often requires extra memory and might not be immediately intuitive. Sorting combined with greedy algorithms is another strategy to consider. Sorting can simplify logic or enable greedy solutions, though it comes with an n log n overhead. The key takeaway is to always start with a simple approach, such as brute force, and then work step by step toward an optimized solution. This clear progression is not only effective but also shows interviewers that you understand the problem deeply. Great job today! We tackled problem number 1968 and discussed possible approaches to solve it. Remember, array manipulation problems are all about understanding constraints and thinking creatively. Keep practicing and exploring new techniques. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!